Hello and welcome to a new session for this ongoing online course on Introduction to Embedded System Design. I am your instructor Dhananjay Gadre. We are going to continue our discussions on using the timer feature of the MSP430 microcontroller in a new mode today. In the past we have seen how to enable the timer, how to use it for measuring time for some duration, and then in a subsequent lecture we saw how we could use the compare function of the timer to compare the value in the timer register with some value stored in the compare registers R1 and R2, and using that feature we were able to generate pulse width modulation signals. Now what we want to do is we want to use the timer for capturing external events or internal events and measure store the value of the timers. So, this is called MSP430 timer in the capture mode. As usual, this is the block diagram of the timer, and let us go through it from top to bottom. Here is our 16-bit timer register. The source of the timer can be an internal clock ACLK or it can be SM clock. And now what I want to introduce to you is an external pin TA clock. That signal can be derived from a pin of the MSP430 microcontroller, which means an external signal would be clocking the timer, would be incrementing the timer, and this would effectively put the timer in a counter mode, because if we do not know the frequency of that incoming signal, all we can say is that we have counted x number of pulses from that signal. We can also divide, once we select what source we want to have, we can divide it with a prescaler here, and then it will be used to feed the clock for the timer. Coming at the bottom, we have 3 compare registers, compare capture registers CCR0, CCR1 and CCR2. CCR0 is very special, as we have seen in the compare lecture in a previous session, that you store a value in the capture compare register 0, and this is used to decide at what time the timer will reset. But now what we want to do is we want to see the capture mode. Now capture mode means that we want to use an external event or an internal event to capture the values of this timer. These values are coming here and they can be captured in this register. They can be captured in R0, capture compare register 0, as well as 1, but this is repeated here. So, that is what is being shown. And what event would capture it? You could have a pin called CCI 2A or 2B for the capture compare register 2. Similarly, you would have pins for CCR1 and CCR0. And you also have this. Now, why do you have a ground and VCC? So that you can generate a signal going from high to low, which you can select the multiplexer, you can set the multiplexer to ground selection, and then when you change it to 1, it would generate a high to low signal. This could be used to capture into this register the value from the timer. Similarly, if you want a high to low, you set the value of this multiplexer to VCC and then you change it to 0 to ground, and this will generate a high to low transition, which could be used to capture the value from the timer into the capture compare register, and then you can do various things with it. You could read the values and so on and so forth. So, in the previous lecture in the compare mode, we use this and use that information of comparison and outputted the signal as a PWM waveform. Now, in this lecture what we are going to do is we are going to see input pins which could be used to create events for the timer. As usual, these are our timer registers. You have timer control register, you have the timer register as it is, which actually counts pulses or signals, clock signals. You have capture compare control register 0, you have capture compare register, capture compare control 1, capture compare 1, capture compare control 2, and capture compare register 2, as well as the interrupt vector register. Now, in the control register, these are the bits. Let us go through these bits relevant to the capture part. As I mentioned, we would like to select the source of the timer. Instead of being internal clock signals, we would like an external pin to provide the signal, and in this case we use these bits TASSELX and select this combination TACLK. This would be mapped to a pin. We will see which one. We could, if you like, you could divide the signal coming there, but we may not want to do that. And then you want to decide whether you want to operate the timer in up mode, continuous mode or up down mode, and then whether you want to have the interrupt associated with the timer and the flag which tells you whether an interrupt is pending or not. Here is the second part of the capture control register, and let us see the bits. Here we want to say, do we want to capture mode or not. Now, in the previous one we said we want to do compare mode. So, the cap bit was set to 0. In this lecture we are going to see how we will set this cap bit to 1 to indicate to the timer that we want to capture. Now, the question is, once you decide that you want to capture, these bits will decide on what event are you going to capture. Are you going to capture on a rising edge or a falling edge, or do you want to capture on rising as well as falling? This option will allow you to do that. And then the source of the signal, that capture signal, is it going to be a pin CCI 1A or 1B or a transition of these two signals? And do you want to synchronize this capture with internal clock? You can select using this. This is the timer control register. We saw this in the previous lecture. These are the output bits, and if you recall, for PWM we selected this combination. But now we want to actually go here, that do you want to have the capture control interrupt enabled? Do you want to find out the value, what is the value of capture input, and in this case whether there is a capture overflow and interrupt flag associated with the capture signal. Now, associated with the various signals, you would have lot of interrupt sources. You have capture compare register 1, register 2 and a timer overflow, and these would be available for both the timers. The timer capture mode, you have to select that we want to do capture. So, CAP is equal to 1. The CCIS bits will decide the capture input, and the capture inputs this or this will be selected, mapped to the external pins. When an event occurs at the input signal, the value in the timer register will be stored in the selected capture compare register 1 or 2 or 0. The CMX bits will select the capture edge of the input signal. Do you want it to on rising or falling, and so on. And if a capture occurs, then the timer value is copied into this register, and the interrupt flag CCI IFG set in this control register, so that an interrupt is generated, provided the global interrupts have been enabled. In the timer capture mode, the state of the selected input can be read in the CCI bit, and to show you where that bit is, let me go back to the block diagram here. This is the CCI bit here. This one. Now, this input can be synchronized to the input clock, or it can be asynchronous. You can choose what you want. Capture events are then synchronized with the next falling edge of the timer clock that follows the trigger midway between increments of the timer register. Now, this is what happens. Your timer clock, whatever be the source, you are going to capture the value into the capture register whenever the appropriate condition arrives. It will capture the value here of the timer into the selected register. Now, why do we want a capture mode? So that many applications require you to measure time between two events. So, the way to do that would be, on first event you capture the value of the timer, let the timer continue operating. Who is going to clock the timer? A known signal internally generated, and then on the second event you capture the second value of the timer, and the difference of the two values will give you the time that has elapsed between two events. This is what is listed in this slide. Now, to illustrate the capture features, we are going to perform an interesting exercise, which is to measure frequency of external signals. For example, there is an instrument called frequency counter. What does a frequency counter do? It measures the frequency of external signals. Of course, if the signal is sinusoidal or triangular, it converts it into a digital equivalent signal, and then using some mechanism it measures the frequency of that signal. Now, to measure the frequency of the signal, obviously you need to measure the pulses, the incoming pulses, for a certain period of time. If your measurement period is 1 second, then the number of pulses you have counted in that 1 second period will give you directly the frequency of the signal. Now, to derive this 1 second reference, you would have an internal clock which must be very accurate, because if the clock is not accurate, that 1 second period will be erroneous and you will infer a wrong frequency. Now, depending upon the source of the clock which is responsible for generating the 1 second period, you have to decide if the incoming frequency that you want to measure is much higher than this clock signal, or is it much lower. If the frequency is much lower, if the frequency of the input signal that you want to measure is much small, very low, then it is better, instead of measuring the period, it is better to measure, instead of measuring the frequency, it is better to measure the period. Once you measure the period, you can do 1 by period to estimate the frequency. If the frequency of the incoming signal, on the other hand, is much higher than the reference timer clock in the measurement instrument, then it is better to measure just the pulses in that 1 second period, and you would directly get the value of the frequency to a resolution of 1 hertz. If you want to have a resolution of 0.1 hertz, what should you do? You must increase your measurement window to 10 seconds and then divide it by 10, so that you know is it 25.1 hertz or 25.2 hertz. So, that is the method of measuring frequency directly. Now, we will see how MSP430 could be used to perform both of these operations, the direct frequency measurement and the period measurement. Now, when you want to do period measurement, we are going to use the timer in the capture mode, and what are we going to do? Here is our reference signal. This reference signal is an internal signal. The idea is that between this period of the unknown signal whose frequency we want to measure, we do not want to measure frequency directly. Instead, we want to measure the period of this signal, and this can be done by counting the pulses of known frequency between the two rising edge of the unknown signal. So, if I know how many pulses I have counted in that one period of the incoming unknown signal, if I know the period of the reference signal, multiplying the count with the period, I get the total period. As an example, suppose the reference frequency inside, reference signal that I have inside is, let us say 1 megahertz. That means the time period is 1 microsecond. And let us say the incoming frequency, I do not know the frequency, I do not know the period. Let us say I enable the counting process, and in that counting process, between the two rising edge of the incoming unknown frequency, from here to here, I accumulate a count of 65,800 counts. Since I know the period of one clock signal of the reference, which is 1 microsecond, therefore, the total period is 65.8 milliseconds, and from here I can estimate the frequency. Therefore, the frequency of the unknown signal is equal to 1 upon 65.8 milliseconds. Now, because we are doing all this in a embedded computer such as MSP430, an embedded computer can very easily perform this calculation. In the olden times, when we did not have computers to perform this, measuring period as a way of measuring frequency was left to just measure the period and display the period, and leave it to the user to note the period and perform this calculation manually to estimate the frequency. But today we do not have to do that. Today we can measure the period and perform a mathematical calculation in the C program to estimate the frequency. And we are forced to do this because the time period here is very, very low. See, if I have a 65 millisecond and if I approximate to 100 millisecond, that means the time, the frequency of this unknown signal is roughly 10 hertz. In the case of 65, it will be about 13 hertz. Now, I want to measure the frequency of this unknown signal, which is round about 13, 10, 20, 10 to 20 hertz, to a accuracy say of first digit. Then I would have to have a measuring window of 10 seconds, so that I count 130 pulses divided by 10 to know whether it is 13.0 or 13.1 hertz. 10 seconds is a very large window. Now, instead of doing that, the period of this 13 hertz signal is 50-60 millisecond. I can easily, which is a very small period, in that I can easily count the number of clock signals of a known signal generated internally, and then estimate the frequency to a second or third decimal place without spending 10 seconds. That is the advantage of measuring the period as a means of measuring frequency. And the rule of thumb is, if the frequency of the unknown signal is much lower than the reference frequency of your instrument, you should measure period. If the frequency of the input signal is much higher than the reference frequency in your instrument, then it is better to measure direct frequency. So, we are going to, in this first exercise, we are going to measure the period of the unknown signal, and from there estimate the value of the frequency. For that, we are going to use timer 0. In the timer 0, the timer itself will be clocked by an internal signal derived out of the A clock. A clock is from the low frequency crystal oscillator, because then it will be accurate, as you know, which is 32,768 hertz, and we divide it by 4, so that we are roughly getting 4 kilohertz, 4096 hertz frequency, which is now going to be used as a reference frequency. We are going to count these pulses into timer register, and the external signal whose frequency we want to measure, the rising edge, at the first rising edge we will capture the timer register value, and on the second we will note this value down in a variable, and then when the second rising edge comes, we will note the timer value again. We know the timer is being clocked with ACLK by 4, so we know the period, and once we know this second count, we take the difference from the first count, multiply it with the period of this reference signal, which is 1 by 4096 hertz, because the frequency is 4096 hertz. So, the time period is 1 by 4096. You will get the period of the unknown signal, and then mathematically you can calculate the frequency also. Now, to be able to measure, obviously I need some source of unknown signal which I can verify. So, what we have done here is we will display the frequency and period on LCD. We already covered how to interface the LCD to our MSP430. In this case, we have used P port 1 pins, and to generate the unknown period or unknown frequency, we have rigged up a 555 based A-stable multivibrator. In fact, the IC used here is 7555, so that it can work at VCC here is 3.3 volts. The VCC for this is 5 volts, as we have gone through this earlier. You remember the LCD works at 5 volts. So, the supply voltage for the 7555 is 3.3 volts and it is used to generate a signal which is available on the output pin 3, and we are going to connect it to P1.2. Why? Because P1.2 will be the capture input, capture compare input, and that will be used to capture the value of the timer into the capture compare register. Now, since we are going to capture the incoming frequency on P1.2, let us see which. Here is the P1.2 signal. We want to select the capture compare register 1. It is an input, so the direction of that is 0, and the rest of the P cell and P cell 2 bits are 1 and 0. That puts P1.2, that is the port 1 bit 2, as timer capture compare input. That is what you have to write in your program. Here is the entire program. I am not going to go through the program. I have already explained the crux of the program. Much of it is about the LCD, which you already seen. Here are the generating the enable pin for the enable signal for the LCD. This is a function to write into the LCD. This is to print values which you have the data, the information that you want to print. This is for printing numbers. This is to set the cursor. This is to initialize the LCD. This is to display the actual frequency values, the period values, and from there calculate the frequency. This is important. This is the register settings for timer 0. What we have done, that we want to use P1.2 as input in the capture mode, and we want to use rising edge. We want to have interrupt enabled, and the source is CCI 0A, which is P1.2, and the clock for the timer is coming from ACLK divided by 4. This is the meaning of this line of code. Here is the main program. As usual, we always disable the watchdog timer. We have initialized the LCD. We have called the subroutine for the timer 0 initialization, and now we are waiting in an infinite loop. This is the infinite loop here. In that we first display something in the LCD which may be initially all wrong. Then we set the status register bits to enter in a low power mode, because we only want to exit the low power mode whenever the interrupt is generated based on the rising edge of the incoming signal, and we have enabled the global interrupt flag. Now we are saying, so these edge 2 and edge 1 are two variables into which the value of the timer registers are going to be stored. If edge 2 value is more than edge 1, now you can calculate the period, and from there you can calculate the frequency and the time period like this. Here is the interrupt vector, the ISR for timer. As we saw, the same interrupt will mean many things could have happened. So, you have to 0 on the right one, and in this case it is capture compare flag being set up, and now there is a internal there is a flag called count. If count is 0, you are going to capture the value of the timer and store it in a variable edge 1. We enable the count to 1, and then next time around when the interrupt happens, which means you are getting the edge 2 values, and then rest of these do not matter, you go back. So, now you have edge 2 value and edge 1 value. From here in the main program you can take the difference, and from there estimate the period, take inverse of it, and you get the frequency. So, this is about measuring the frequency of incoming signal, which is estimated to be a low frequency. So, instead of measuring the frequency directly, you measure the period. Here is the setup. As you see here, the frequency is very low, as an example 18 hertz, and you see now this is the information given by the oscilloscope, which may not give very accurate values. Here we see the frequency is actually 18.28 hertz. Ignore the period part because it is not printing the second decimal or third decimal in this case. Here is the LCD, the setup for the LCD, and here is the setup for the 7555 to generate the unknown signal. Here is a potentiometer, so that we can vary the frequency and measure it on P1.2 and display the value here. This is the setup for the period measurement. As I discussed earlier, if the frequency of the incoming signal is high, then instead of measuring the period, you can directly measure its frequency by enabling a mechanism to count the incoming pulses for 1 second period. All right. Let me go back here and maybe recall this again. So, imagine that you have a AND gate, okay, and here is your incoming signal, whose frequency you want to measure. Imagine the second signal is a 1 second pulse. Now, because this is a AND gate, it is going to allow incoming signals to pass here, which could be high frequency like this, and therefore, you are going to get nothing and then high frequency for 1 second and so on. So, if this signal you feed it to a counter, the counter at the end of for this one period is going to give you the frequency. On the other hand, if the incoming frequency is very low, then you do the following: you bring the incoming signal, divide it by 2. Why do I divide it by 2? So that I can get high for this and then low for the same period. So, in this one entire period of the unknown signal, I measure a in-house high frequency reference signal. Now, what will happen? I do not know this period, this is some value t, but I know the frequency of this, which is being generated internally. So, if I count how many pulses I have accumulated in this time period, I can estimate the value of this t. So, this is the period measurement and this is the frequency measurement. We already seen the period measurement earlier. Now, let us see how do we measure the frequency directly. We create internal reference signal of 1 second. Now, we can't do both of these things using a single timer. So, for frequency measurement, we are forced to use 2 timers. We are going to put the unknown signal on the input pin of the timer. Instead of an internal clock signal, we are going to derive it out of a external pin, and in that case it is TACLK. We will see which pin it maps to, and this is going to clock timer 0, and we are going to generate 1 second reference signal on timer 1. That is the meaning of this setup. This is our unknown signal. This is our unknown signal here, whose frequency we do not know, but we know that internally we are able to generate 1 second reference period, which we are going to generate from timer 1, and the incoming signal, unknown signal, we are going to feed to timer 0 directly into the timer, and using we are going to generate interrupt here, read the timer 0 value, store it, and when the second interrupt happens, here this time in the falling edge, we are going to capture the value of timer 0 again, and the difference will be the frequency directly. Why? Because this period is 1 second. Again, for the setup, we have created a mechanism to display on a LCD, same as past, and we have created a source of frequency which we can measure, but instead of in the previous one the unknown signal being generated out of this 7555 IC, it is in the astable multivibrator mode, by the way, both the cases. Here the frequency is higher, and that you can how do I ensure that? Let me go back to the previous setup here. The period of that astable multivibrator is decided by this capacitor. As you see, this is 1 microfarad. Compare this with the frequency with the capacitor of this timer 555. Here it is 1000 picofarad, 1 nanofarad, and so the frequency that will be generated here will be much higher than the previous case. Instead of putting that unknown frequency on P1.2, we have to now put it on P1.0. Why? Because this is going to feed the TACLK signal of timer 0. Our signal is going to come from P1.0 and we see P1.0 this. So, we have, and this is an input now, and so the direction is 0 and the select the P1 cell and P1 cell 2 bits are 1 and 0. This is what we have to program the port 1 register. Here is the program for doing that. Again LCD part, the writing of the LCD, the setting of the cursor here. This is to initialize the LCD in 4-bit mode, to display the value directly the frequency here, and here is the register setting for timer 1, which is important because that is going to generate the 1 second period. This is the main program. Since we are generating the 1 second period from the low frequency crystal, we have to wait for it to stabilize. Then bit 0 is the input, P1.0. So, that we have decided as input. Then we have initialized the LCD and we have called the function for timer 1 as we saw here, and now we are waiting. Once the interrupt happens, you are going to go in this interrupt subroutine and you are going to directly capture the value of the timer 0 value and use that as the count, which is directly the frequency. Here is the setup. As you see here, the frequency of this unknown signal from the 555 is estimated to be 26.6 kilohertz, and the actual frequency down to 1 hertz resolution measured by our setup is 26675 hertz. So, we have seen how the timer modules in the MSP430 microcontroller could be used for capturing external signals, and using these modes you can measure frequency and period of unknown signals, which is a very important activity oftentimes in embedded applications. So, this completes the timer capture mode, and I will see you very soon with a new lecture. Thank you.